Hello students, from past few classes we are studying the article closed sets and limit points. Particularly in the last class we have defined the limit point of a set in a topological space. Then we have also defined the limit point of a set in the subspace of a topological space. We have also discussed two important results about the limit point of a set in the topological space as well as in the subspace of a topological space. Now, in the today's class, we are going to study the next important article, and it is the Hausdorff spaces. So, the next article is the Hausdorff spaces, and in this article, we are going to define Hausdorff space. The definition of a Hausdorff space we are going to study. Then we are going to consider explanation of Hausdorff space by drawing a diagram. Then we will go for some results about the Hausdorff spaces. So, let us begin with the definition of a Hausdorff space. Hausdorff space is defined as a topological space X is called a Hausdorff space if for each pair x1, x2 of distinct points from the topological space X, there exist neighborhoods u1 and u2 of points x1 and x2 respectively, such that they are disjoint. See here how we are defining the Hausdorff space. A topological space X will be called as the Hausdorff space if for each pair x1, x2 of distinct points of X, means if x1 and x2 are any two distinct points from the topological space X, then there must exist the neighborhoods of x1 and x2 as u1 and u2, such that these neighborhoods must be disjoint, means u1 intersection u2 must be empty set. That is, for every pair x1 not equal to x2 in the topological space X, there must exist neighborhoods u1 and u2 such that u1 intersection u2 is equal to phi. Like such, the Hausdorff space is defined. Now, for understanding purpose, consider the diagram which is drawn here. See here, suppose this outer rectangle is our topological space X, and x1 and x2 are any two distinct points from the topological space X, then if there exist neighborhoods u1 of x1 and u2 of x2 such that u1 intersection u2 is empty, then clearly that topological space X will be called as the Hausdorff space. Okay, one example of this we will consider here. So let us suppose that we have the set Z plus of positive integers. Z plus is the set of positive integers, means members of Z plus are 1, 2, 3, 4, 5 and so on. So these are the members of the Z plus. Then definitely this is a subset of the R. Okay, we know that Z plus is the subset of R, means the set of real numbers. Next one, observe here, this is our R, means the real line. Next one, if we take any two members distinct from this Z plus, for example, suppose here it is 2 and somewhere here it is 5, then as 2 and 5 are the distinct points from the set Z plus, then we can consider that if we take a very small length, then there exist intervals, means the neighborhoods of 2 and 5 such that these two neighborhoods does not intersect each other. Similarly, if we take some another points such as 3, 4 and so on also, again we can consider the neighborhoods of these points also such that they do not intersect each other. So, neighborhood of 2 do not intersect neighborhood of 3, neighborhood of 3 do not intersect neighborhood of 4, neighborhood of 4 do not intersect neighborhood of 5, neighborhood of 2 do not intersect neighborhood of 4, neighborhood of 2 do not intersect neighborhood of 5 and so on. So from this it is clear that this set Z plus, this topological space Z plus, means the set of positive integers. It is a Hausdorff space. So like such we have the Hausdorff space, its a definition and explanation. Now we will prove some important results about the Hausdorff spaces. First important result about the Hausdorff space is Theorem 6.8, and statement of this theorem is every finite point set in a Hausdorff space X is closed. means every finite point set in a Hausdorff space is closed. That we have to prove here. Okay, and to prove that every finite point set in a Hausdorff space is closed, it is sufficient to show that every singleton set, means one point set in Hausdorff space, is closed. So we will show in this way. This is our plan of action. So proof of this is, let X be a Hausdorff space. Then definition is known to us of the Hausdorff space. Next, then to prove the theorem, it is sufficient to show that every one point set, suppose that one point set is the singleton set containing the point x0, is closed. So if we are able to show that every singleton set x0 is closed in the Hausdorff space, then the result follows. Next one, if X is a point of Hausdorff space X different from x0. So let us consider a point X from the Hausdorff space capital X, which is different from x0, means that is X is not equal to x0, where X and x0 are two distinct points from the Hausdorff space X. Then use the definition of the Hausdorff space, as X and x0 are the distinct points from the Hausdorff space. Therefore, there exist neighborhoods of X and x0 such that those neighborhoods do not intersect each other, means they are disjoint. Okay, then as X is a Hausdorff space, therefore by the definition of the Hausdorff space, X and x0 will have disjoint neighborhoods. Suppose the neighborhood of X is U and neighborhood of x0 is V respectively. Next, now as U does not intersect x0, by definition of Hausdorff space, as U and V are the neighborhoods of X and x0, and X and x0 are the distinct points, therefore U will not intersect the singleton set x0. U will not intersect V, and subset of V is singleton x0, therefore U does not intersect singleton set x0, and therefore point X cannot belong to the closure of the set x0. Okay, the point X cannot belong to the closure of the set singleton set x0. Why it is so? Because in the last class in the theorem 6.5 we have proved that X will be limit point of a set if it belongs to the neighborhood of that set. Okay, if X belongs to the every neighborhood of a set, suppose set A, then and then X will be limit point of the set A. So next one, therefore for any X different from x0 cannot belong to the closure of the set singleton x0. Means if we take any point from the Hausdorff space which is different from the set x0, then that point cannot belong to the closure of the set x0, and this implies that the closure of the set singleton x0 is the singleton set x0 itself. Means the closure of this singleton set x0 consists of only one point, and that point is the singleton, that point is x0 itself. Means this singleton set x0 do not have any point in its closure other than x0 itself, which means that the set singleton x0 is closed. Why it is closed? Because this set and its closure, they are equal. Closure of the singleton x0 is equal to the singleton x0. So as the set equals its closure, therefore that result also we have studied in the last class, that if A is a set such that A is equal to A bar, where A bar is the closure of the set A, then the set A will be closed. So here we have shown that the singleton set x0 has its closure same as the singleton set x0. So therefore by that result we conclude that the singleton x0 is closed. So we have shown that every singleton set in a Hausdorff space is closed, and as we have told earlier, as every singleton set x0 in a Hausdorff space is closed, therefore this implies that every finite point set in a Hausdorff space is closed. By the finite point set we mean finite set. Okay, so therefore in this way we have proved that every finite point set in Hausdorff space is closed. This is that important result. Now next one we will state another important result. Now next important result is the theorem 6.9. Let X be a Hausdorff space and let A be a subset of the Hausdorff space X. Then the point small x is a limit point of set A if and only if every neighborhood of X contains infinitely many points of A. I will repeat, let capital X be a Hausdorff space and let capital A be a subset of X. Then the point small x will be a limit point of the set A if and only if every neighborhood of X contains infinitely many points of the set A. If you remember, in the semester 5th paper metric spaces, many times we have studied such results. Most of these results are studied in the metric spaces paper, and this is also one of those results. Now next, after this result, we will prove one important result about the Hausdorff spaces from the exercises. So the next example is, show that the product of two Hausdorff spaces is Hausdorff. We have to show that the product of two Hausdorff spaces is Hausdorff. So we will prove this one. To show that the product of two Hausdorff spaces is Hausdorff, we have to consider first of all two Hausdorff spaces, and then we have to show that the product is again a Hausdorff space. Then to show that the product is also a Hausdorff space, we have to consider two distinct points from the product, and we have to show that their neighborhoods are disjoint. So we will solve this one. Let X and Y be two Hausdorff spaces, and A1 cross B1 and A2 cross B2 be two distinct points in the product X cross Y. First of all, we have supposed that X and Y are two Hausdorff spaces, and A1 cross B1 and A2 cross B2 are two distinct points from the product set X cross Y. Next, as we have supposed that A1 cross B1 and A2 cross B2 are two distinct points from the product space X cross Y, this means that either A1 is not equal to A2 or B1 is not equal to B2, because if A1 is equal to A2 and B1 is equal to B2, then and then only A1 cross B1 will be equal to A2 cross B2. This is very well known to us. Okay. Next one. So first of all, we will consider the case that A1 is not equal to A2, and this other case B1 is not equal to B2 can be stated similarly. So let us suppose that A1 is not equal to A2, means A1 and A2 are suppose distinct points from the topological space X, and the topological space X is Hausdorff space by our supposition. Okay. So let us suppose that A1 is not equal to A2. Next, then as X is a Hausdorff space and A1 and A2 are distinct points from the Hausdorff space X, therefore by the definition of Hausdorff space, there exist open sets. Open sets means neighborhoods U1 and U2 of points A1 and A2 respectively in X, such that A1 belongs to U1 and A2 belongs to U2, means U1 is a neighborhood of A1 and U2 is a neighborhood of A2, and this exists in such a way that their intersection is empty, means they are disjoint. So such that U1 intersection U2 is empty. This is by the definition of Hausdorff space, which we have studied just 2 minutes before. Okay. So such open intervals means neighborhoods exist of A1 and A2. Next one. Now, as U1 and U2 are neighborhoods, means they are open in X and Y, and we know that every topological space is open in itself. So therefore Y is open in Y. So as U1 is open in X and Y is open in Y, therefore U1 cross Y is open in X cross Y. This is very well known to us by the product space. Product topology we have studied earlier. From that article we know that if U1 is open in X and V1 is open in Y, then U1 cross V1 is open in X cross Y. Here instead of V1 we are considering Y, and Y is open in Y, that is known to us. We have used this many times. So as U1 is open in X and Y is open in Y, therefore U1 cross Y is open in X cross Y. Similarly, as U2 is open in X and Y is open in Y, therefore U2 cross Y is again open in X cross Y. Now U1 cross Y as well as U2 cross Y both are open in the product space X cross Y. Therefore their union will be again a open set in X cross Y. Next, now A1 cross B1 belongs to the U1 cross Y, which means that U1 cross Y is an open set in X cross Y which contains A1 cross B1, means U1 cross Y is open set containing the point A1 cross B1, which means that U1 cross Y is a neighborhood of point A1 cross B1. Similarly, A2 cross B2 is contained in the point. Similarly, the point A2 cross B2 belongs to the open set U2 cross Y, and U2 cross Y is open set. Therefore, U2 cross Y is a neighborhood of point A2 cross B2. So, therefore, U1 cross Y is a neighborhood of A1 cross B1, and U2 cross Y is a neighborhood of A2 cross B2. And again, the intersection of these two sets, U1 cross Y and U2 cross Y, is empty. Why it is so? Observe here. We have U1 cross Y intersection with U2 cross Y. It will be equal to the, by the set theory, we have U1 cross Y intersection with U2 cross Y is equal to the U1 intersection U2 cross Y. Next, now as U1 intersection U2 is empty, so put for the U1 cross U2 as empty set phi. So this will be equal to the empty set phi cross Y. And we know that the Cartesian product of empty set with any set is always the empty set. So therefore, this is equal to the empty set phi. So what we have shown, so for any two distinct points A1 cross B1 and A2 cross B2 from the product space X cross Y, we have obtained two neighborhoods U1 cross Y and U2 cross Y of the points A1 cross B1 and A2 cross B2 such that their intersection of these two neighborhoods is empty. So this implies that by the definition of the Hausdorff space, this implies that the product space X cross Y is a Hausdorff space. So we have shown that whenever A1 and A2 are two distinct points from the Hausdorff space X, then X cross Y is a Hausdorff space. Now similarly, we can show that if B1 is not equal to B2, then also we get X cross Y as a Hausdorff space. We have shown for A1 not equal to A2. Similarly, if A1 equal to A2, even though if B1 is not equal to B2, then also we'll get that X cross Y as a Hausdorff space. Therefore, from both these parts, we conclude that the product of two Hausdorff spaces is again a Hausdorff space. So in this way, we have proved this result. Similarly, we have one more result, and that result is the subspace of the Hausdorff space is again a Hausdorff space. And it is the homework for you. You can prove that the subspace of the Hausdorff space is again a Hausdorff space. So in the today's class, we have defined the Hausdorff space. We have gone through the concept of the Hausdorff space. We have explained the concept of Hausdorff space by drawing the diagram. And we have then studied three important results about the Hausdorff spaces. So with this, we'll stop here and we'll continue in the next class. Thank you.